In this video, we will learn about applications of nuclear chemistry and also how half-lives work. All right, first up, we're going to talk about different ways where exposure to radioactivity is detected and also monitored. And so the first method is known as a Geiger counter. And so Geiger counters detect radioactive rays because the air becomes ionized. And so they count when argon gas atoms are ionized by radioactive waves. And so a Geiger counter will emit a beep every time it happens. But anyway, that's more of a live radioactive decay system. It will emit a beep sound so that you can tell how close you are, and how the more often the beeps happen, the closer you are to a radioactive source. So the second method is more of a passive way of monitoring how much a worker is exposed to radiation. And so workers that work around radiation are required to wear a film badge. And I've worn a film badge before. It's nothing to worry about being asked to have to wear one. It's to monitor how exposed you've been in the event of an accident. Um, and every few months, the badge has to be sent in for reading, and then it's replaced with a new one. And so there's a light film on it, photographic film, to detect how much radiation you've been exposed to. And so natural radiation is natural. It's not just occupations that can expose you to radiation, but just living your everyday life, because there are naturally occurring radioactive isotopes. For instance, one radioactive isotope is potassium 40. And so that's a naturally occurring isotope of potassium. So anything containing potassium, including you and bananas, contain potassium 40. That's a naturally occurring isotope of potassium. It's always been there. So every banana you've ever eaten, every person you've been near, has contained potassium 40. Also in you and all living things. And all living things is carbon 14. Carbon 14 is a naturally occurring isotope of carbon, and so being near other people does give you some radiation exposure. But just being outside can also give you radiation exposure, because there's also radiation from outer space. There's cosmic radiation. A lot of it's absorbed from the ozone layer, and so that's why that hole in the ozone layer was a big problem. But even if the ozone layer is fully there, just being higher up in the atmosphere will expose you to more cosmic radiation, because there's less atmosphere to block and scatter and absorb that radiation. So being a flight attendant is actually an occupation that will expose you to quite a bit of naturally occurring cosmic radiation. And down at the ground level, there's also radiation from soil and different naturally occurring radioactive isotopes in soil. So there are applications of radioactive isotopes, including dating rocks and fossils. You might have heard of radiocarbon dating. Carbon dating, that uses carbon 14. So carbon 14 is used for dating fossils. And then generating power. So this uses nuclear fission. the sun uses nuclear fusion. And then there's different types of medical imaging that use radioactive isotopes or for treatment of cancer. There's also radiation treatments. The atomic bomb was a not so great use of radioisotopes in nuclear chemistry. And then too much can also destroy human tissue. So Marie Curie actually died of radiation poisoning. These different modes of radioactive decay, like alpha particles, beta and gamma, those different modes of decay have different penetrating power and different ionizing power. And it's really interesting to look at the trend to figure out the pattern. So alpha particles are very massive, and so they have a hard time penetrating through objects. Gamma rays are electromagnetic radiation, so they can't penetrate. They have no mass at all. And so those are very energetic. So gamma rays can penetrate through objects. They can penetrate through your hand, they can penetrate through a sheet of aluminum, and it takes like a lead vest to block them. So that's why they ask you to wear like lead vests when you're getting some objects or some medical things done. It's to try to block some radiation exposure. And then like alpha particles, since they are so highly charged, they are very ionizing. So just because they don't penetrate very far, you might think, oh, they're easy to block. They are easy to block, but they do ionize more than gamma radiation. Gamma rays have the lowest ionizing ability because they are not charged. So it's kind of inversely. And if we think about positrons, positrons fall in close to the beta particles in the middle because they are very similar, and we actually could use the beta plus symbol for the positron. Another interesting note is occupational safety. If you want to read a book about occupational safety and the development of it, The Radium Girls is a book about women who were hired to work in factories in the early 1920s painting watch dials, and they would use radium laced paint in order to paint the watch dials. And they were instructed, in order to get a fine brush tip point, to use their lips to smooth the brush into a fine tip. This caused them to get paint on their lips and in their mouth, and that led to jaw necrosis and cancer and bones just like decaying rapidly. And they ended up suing their employers, and it was quite a dragged out process because the effects of radiation poisoning were just not well understood at the time. Radium had only been discovered about 20 years prior to these factories opening, so it hadn't been around long enough for people to really understand the side effects of radiation. Okay, so let's talk about half-lives and half-life applications. Maybe I'll just make this a second video.